Prove that the pressure exerted by a gas is P equal 1 by 3 rho V RMS square, where rho is the density of the gas, and VRMS is the root mean square velocity of the different of n number of gas molecules. VRMS is the root mean square velocity of gas molecules. For this, we can consider a cubical container in which there are n number of gas molecules of an ideal gas. We can consider the three-dimensional axis, that is x, y, z, and O be the origin. And at the origin O, we can consider a cubical container containing ideal gas. ABCD is a vertical wall. Similarly, OGHJ is another vertical wall of the cubical container. This is the cubical container containing ideal gas. This is the cubical container. ABCD OGHJ is a cubical container containing an ideal gas of mass capital M and volume V. This is a gas molecule. This is a gas molecule of mass M. Small m is the mass of each gas molecule. And this is the first gas molecule. We can assume that this molecule is the first gas molecule which is moving with a velocity v1 along this direction. Similarly, second gas molecule having the same mass m will be moving with a different velocity v2 along this direction. And we have to assume that different gas molecules of the ideal gas will move with different velocities. According to kinetic theory of gases, obviously gas molecules will be moving with different velocities ranging from 0 to infinity. So in this case, the velocity of the first gas molecule, that is v1, will have three rectangular components of velocity along x, y, and z axis. v1x is the rectangular component of velocity v1 along x-axis. v1z is the rectangular component of velocity along z-axis. And also we can consider the rectangular component of this velocity v1 of the first gas molecule along y-axis as v1y. We can denote the length of each side of the cube. L is the length of each side of the cube, or length of each face of the cubical container. So L is the length of the plane DCHJ, and we can denote the length of the other sides of the cubical container. L is the length of each side of the cubical container. In this way, we can denote the length of each side of the cubical container. Let v1, v2, vn be the velocities of n number of gas molecules of an ideal gas contained in OGHJ ABCD cubical gas container. v1, v2, vn be the velocities of n number of molecules of an ideal gas contained in the cubical gas container of each side L and having volume of the cube as V equal L cube, as V equal L cube. The rectangular components, the rectangular components of the velocity, the rectangular component of the velocity V1 of the first gas molecule, are given by V1x, V1x, V1y and V1z, V1x, V1y and V1z along x, y and z axis respectively. The rectangular components of the velocity V1 of the first gas molecule are given by V1x, V1y and V1z along x, y and z axis respectively. We can assume that the first gas molecule of mass m1 is moving with a velocity v1x along x-axis towards the wall ABCD of the cubical container, and after the elastic collision, the same gas molecule will be reflected with the same velocity v1x. The first gas molecule undergoes an elastic collision with an initial linear momentum p1x prime as mv1x, and it undergoes elastic collision with the vertical wall ABCD, and it will be reflected with the final linear momentum p1x f prime as equal mv1x, and also we can denote the x-axis, In the diagram, the first gas molecule is moving with an initial linear momentum p1x prime as equal mv1x, undergoes an elastic collision with the vertical wall ABCD, and this is the vertical wall of the cubical container, and after the elastic collision, the same gas molecule will be reflected back with the final linear momentum p1x f prime is equal to minus mv1x. According to the kinetic theory of the gases, the first gas molecule, that means this first gas molecule undergoes an elastic collision perpendicularly to the vertical wall ABCD. The first gas molecule undergoes an elastic collision with the vertical wall ABCD of the cubical container. With an initial linear momentum p1x I prime as equal mv1x along x-axis, and rebounds with the final linear momentum p1x f prime is as equal minus mv1x along negative x-axis. Therefore, the change in linear momentum of this first gas molecule, the change in linear momentum of the first gas molecule along x-axis after one collision is given by delta p1x prime. Delta p1x prime will be equal to p1x f prime minus p1x I prime. equal minus mv1x minus mv1x equal minus 2mv1x. Therefore, delta p1x prime is equal minus 2mv1x minus 2mv1x, which is the change in linear momentum of this first gas molecule due to the elastic collision of this first gas molecule due to this elastic collision. And in this expression, negative sign indicates that this gas molecule, that is the first gas molecule, will be moving along negative x-axis, after the elastic collision with the vertical wall ABCD. Again, according to the law of conservation of linear momentum, the change in linear momentum transferred, that is imparted to the vertical wall ABCD of the cubical container, imparted to the wall ABCD due to this elastic collision of the first gas molecule with the vertical wall ABCD, is given by delta p1x is equal to minus delta p1x prime is equal minus 2mv1x. Therefore, delta p1x is equal to 2mv1x. Delta p1x is equal to mv1x. This is the change in linear momentum transferred to the wall ABCD. This is the change in linear momentum imparted to the wall ABCD by the first gas molecule, or this is the change in linear momentum imparted to the wall when the first gas molecule undergoes elastic collision with this wall. Now we can denote negative x-axis or a direction opposite to x-axis, and here delta p1x prime is along negative x-axis and delta p1x is 2mv1x, which is the change in linear momentum imparted to the wall, and delta p1x prime is the change in linear momentum of the first gas molecule as it undergoes an elastic collision with the vertical wall ABCD, and delta p1x is the change in linear momentum transferred or imparted to this vertical wall ABCD by the first gas molecule. Change in linear momentum of the gas molecule occurs along negative x-axis, and change in linear momentum which is imparted to the wall will be along positive x-axis. Therefore, the force exerted on this wall ABCD due to the bombardment of the first gas molecule with this wall, the force exerted on this wall ABCD of the cubical container due to bombardment of this first gas molecule with this wall, or the cubical container by the first gas molecule along x-axis, is given by f1x is equal delta p1x divided by delta t, which is the force exerted on the wall ABCD due to bombardment of this first gas molecule with the vertical wall ABCD. So we get f1x which is equal to delta p1x divided by delta t, where delta p1x is the change in linear momentum imparted to the wall, and delta t is the interval of time in which delta t is the interval of time in which the gas molecule, the first gas molecule, in which this first gas molecule undergoes delta t is the interval of time in which this first gas molecule undergoes, where delta t is the interval of time in which the first gas molecule undergoes two successive collisions with the two vertical walls or two opposite walls ABCD and OGHJ of the cubical container after traversing a distance 2L. Therefore, delta T is equal to total distance traveled by the first gas molecule when it undergoes two successive collisions divided by velocity of this gas molecule along x-axis. And in the numerator we should have the distance traversed by this gas molecule or by the first gas molecule between two successive collisions of this gas molecule with the vertical walls ABCD and OGHJ respectively. Therefore, delta T is equal to L divided by V1x. Delta T is equal to L divided by V1x, and where L is the length of each side of the cube and V1x is the rectangular component of velocity V1 of the first gas molecule, and we get the equation 2, which is delta T is as equal to L by V1x. In the diagram, we can denote the first gas molecule which started its motion from the wall OGHJ. The first gas molecule is traveling with a velocity V1x with the rectangular component of velocity V1x along x-axis, and it undergoes first elastic collision with the vertical wall ABCD, and it will be reflected back with the same velocity or with the same rectangular component of velocity V1x, and at this moment this first gas molecule undergoes second elastic collision with the vertical wall OGHJ, and the total distance traversed by this first gas molecule will be L plus L. L is the distance during forward motion, and L is the distance traveled by the first gas molecule after the reflection to reach the same wall OGHJ after the first elastic collision. Putting the expression of delta T or interval of time from equation 2 in equation 1, we get F1x is equal, it was delta P1x divided by delta T, where delta P1x is the change in linear momentum which is imparted to the vertical ABCD. Putting the expression of delta T, we get F1x as equal delta P1x divided by 2L by V1x, where delta P1x is equal to 2m V1x, which is the change in linear momentum imparted to the wall ABCD, with which the first gas molecule undergoes the first elastic collision. Delta P1x is equal to 2m V1x, which is the change in linear momentum imparted to the wall ABCD, equal 2m V1x divided by 2L by V1x. 2m V1x divided by 2L by m V1x. So finally we get f1x as equal m v1x squared divided by m v1x squared divided by L, where L is the length of each side of the cubical container. f1x is equal m v1x squared divided by L, m v1x squared divided by L, which is the force exerted, on the wall ABCD by the first gas molecule as it undergoes the first elastic collision with this wall along x-axis. In the diagram, the first gas molecule of mass m is moving towards the vertical wall ABCD, and it is moving with a velocity v1x and undergoes the first elastic collision and apply a force f1x. f1x is the force exerted by the first gas molecule to the vertical wall ABCD. Therefore the total force exerted by all the gas molecules to this wall ABCD along x-axis will be what? The total force exerted by all the gas molecules on the vertical wall ABCD will be Fx is equal f1x plus f2x plus f3x plus dot plus fnx, where f1x is what you know, force exerted by first gas molecule, and f2x f3x fnx are the forces exerted by the second, third, nth gas molecule with the vertical wall ABCD along x-axis. Fx is the force exerted by all gas molecules on this wall, on the vertical wall along x-axis. So we get m v1x square by L plus m v2x square by L plus m v3x square by L plus plus m vnx square divided by L, where L is the length of each side of the cube, equal m by L bracket open m v1x square plus v2x square plus v3x square plus plus vnx square, where v2x v3x vnx are the rectangular components of the velocity v2 v3 vn of second, third, nth gas molecule along x-axis. Now we can consider the diagram again, and here what we can write. In the diagram, we can show that the first gas molecule is moving towards the vertical ABCD with a rectangular component of velocity v1x. Similarly, the second molecule or another gas molecule will be traveling towards the same vertical wall with the rectangular component of velocity v2x. And also you can denote the pressure exerted by these gas molecules on this wall ABCD can be denoted by P1x and P2x, and we get the total pressure Px along x-axis. P1x and P2x are the pressures exerted by the first and second gas molecule on this wall ABCD along x-axis, and we get the resultant pressure Px applied on this vertical wall ABCD by n number of gas molecules. Therefore the pressure exerted on the vertical wall ABCD of the cubical container by n number of gas molecules of the ideal gas along x-axis is given by Px is equal P1x plus P2x plus dot 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 dot, and Px is the pressure exerted by the n number of gas molecules along x-axis, which is equal to force exerted divided by area of this vertical wall ABCD, equal Fx by L square. Putting the expression of Fx, we get 2 by L square m by L under bracket V1 x square plus V2 x square plus dot 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 plus Vn x square. M by L cube bracket open V1 x square plus V2 x square plus dot 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 plus Vn x square, which is the pressure exerted by the number of gas molecules along x-axis. Px is equal to m by L cube bracket open V1 x square plus V2 x square plus dot 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 plus Vn x square, which is the pressure exerted by the n number of gas molecules on this wall ABCD along x-axis. Similarly, the pressure exerted by n number of gas molecules exerted by the gas molecules on this wall, the pressure exerted by the gas molecules on the wall CHJD and CHJD and CHGB, CHJD and CHGB of the cubical container. In this case, CHJD and CHGB are the walls which are perpendicular to y-axis and z-axis, are given by the pressure exerted by the gas molecules on the wall CHJD and CHGB are given by Py equal m by L cube bracket open V1 y square plus V2 y square plus dot 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 plus Vn y square. Pz, which is the pressure exerted by the gas molecules along z-axis, is given by m by L cube under bracket V1 z square plus V2 z square plus dot 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 plus Vn z square, where V1y, V2y, dot 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 Vny are the rectangular components of velocities of n number of gas molecules of an ideal gas along y-axis. Gas molecules along y-axis, and V1z plus V2z dot 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 Vnz are also the rectangular components of velocities of n number of gas molecules along z-axis. Py is equal to m by L cube and Pz is equal to m by L cube under bracket V1 z square plus V2 z square plus dot 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 plus Vn z square. Since the molecular density of the gas is uniform throughout the cubical gas container, the pressure, since the molecular density of the gas is uniform throughout the gas, the pressure exerted by the gas molecules is same in all the directions. The molecular density of the gas is uniform throughout the gas. That's why pressure exerted by the gas molecule is same in all directions. So we can denote the pressure exerted to the wall ABCD along x-axis as Px, and pressure exerted by the gas molecules along z-axis can be denoted by Pz. Pressure exerted by the gas along y-axis can be denoted by Py. We have three pressures in three different directions, that is Px, Py and Pz. Hence Px will be equal to Py will be equal to Pz equal to P. That is assumed. These three pressures in three different directions are equal and they are denoted by P. common pressure P, and therefore the pressure exerted by the gas molecules, in a particular direction, that means along x-axis or along y-axis or z-axis, is given by P equal one third of 3P, one third of P plus P plus P, equal one third of P plus P plus P, equal, here Px is the pressure acting along x-axis, Pz and Py are the pressures acting along z and y-axis here, and these pressures are same. Therefore, you can say that Px equal Py equal Pz, equal one third Px plus Py plus Pz, because Px is equal Py equal Pz equal P. And finally, we get the expression of pressure exerted by the gas as one third Px plus Py plus Pz. Px plus Py plus Pz. That is the pressure exerted by the gas molecules in a particular direction. P equal 1 by 3 under bracket m by l cube, bracket open, b1 x square plus b1 y square plus dot 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 plus bn x square plus m by l cube, bracket open, under bracket, what we can write, v1 y square plus v2 y square plus dot 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 plus vn y square plus m by l cube, bracket open, v1 z square plus v2 z square plus dot 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 plus vn z square, equal one third m by l cube, under bracket we can write v1 x square plus v1 y square plus v1 z square plus v2 x square plus v2 y square plus v2 z square plus dot 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 plus bracket open, v1 x square plus vn y square plus vn z square, bracket closed, equal m by capital V, where capital V is the volume of the cubical container, under bracket v1 square plus v2 square plus dot 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 plus vn square, where vector v1, that is the velocity vector of the first gas molecule, is equal v1x I cap plus v1y j cap plus v1z k cap. Vector v2 is the velocity vector of second particle, which is v2x I cap plus v2y j cap plus v2 z k cap plus dot 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 v, and then we can write down vector vn, which is equal to vnx I cap plus vn y j cap plus vn z k cap, and v equal l cube, which is the volume of the cubical gas container of the ideal gas, v equal l cube, which is the volume of the cubical container of the gas, equal one third m capital N by v, v1 square plus v2 square plus dot 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 vn square divided by n, where n is the total number of gas molecules, one third capital M by v, under bracket v1 square plus v2 square plus dot 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 vn square, whole divided by n, where capital M is the total mass of the gas, and capital M is the total mass of the gas, and small m is the mass of each molecule of the gas, equal one third rho vrms square. P equal one third rho vrms square, where rho is the density, which is the ratio of total mass m divided and volume v. Rho equal m by v, which is the density of the gas, We get the expression of pressure P, which is one third rho vrms square, and this is the pressure exerted by the gas molecules in a definite direction or in a particular direction. P equal one third rho vrms square, which is the pressure exerted by the gas molecules in a definite direction, and P is equal one third rho vrms square, where Vrms is the root mean square velocity of n number of gas molecules, such that Vrms is the root mean square velocity of n number of gas molecules, such that Vrms is equal root over, and Vrms is equal root over v1 square plus v2 square plus dot 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 plus vn square whole divided by n, and that is the RMS root mean square velocity of n number of gas molecules. And we get the expression of total pressure exerted by the gas molecules in a particular direction, that is P is equal 1/3 rho v RMS square. We get the pressure exerted by the gas molecules in a definite direction as P equal 1/3 rho v RMS square. P equal 1/3 rho v RMS square.